Thank you for inviting me, and thank you for coming to this seminar. So today's topic is mathematics of quantum many-particle systems. So you can think it as a branch of mathematical physics. So in this talk, I'm going to briefly explain what mathematical physics is, especially for this subject. And that explanation will be through one or two examples that I wrote and I studied so far. So, I Googled mathematical physics before I come here. And, there are two quotes I liked most from the search result. So the first one is that according to Journal of Mathematical Physics, mathematical physics is the application of mathematics to problems in physics and the development of mathematical methods suitable for such applications and for the formulation of physical theories. So the keywords here is the application of mathematics to problems in physics and the formulation of physical theories. And the second quote was what I liked most. It's from Walter Thirring, mathematical physics, and in one of his books, he said, his studies work from the basic laws. Here the basic laws usually means the basic laws of quantum mechanics or some other fields of physics. So from the basic laws to derive physically relevant results with full mathematical rigor. So you can put quotation mark to this full mathematical rigor because that's what mathematical physicists believe the most important. So here's the first example, mean field limit and Hartree equation. So we only have 4 basic laws. So the first one is that the particles are the coordinates in R3 from x1 to xn. So we have n particles if you think it as a physical system. And if you think it as a mathematical problem, then you have n variables, and each of them is in R3. And the wave function, physically it describes a given system, and mathematically it's just a function in L2. So because we have n variables in R3 psi, the wave function must be in L2 of R3n. And Hamiltonian is, physically it means energy, and mathematically it means just an operator. So this operator is written by this minus Laplacian for each particles from I equals 1 to n, and the potential term. So here we have 1 over n, and that is what you call mean field limit. So basically we want to take an average of n particle. And the interaction or the potential is only described by the potential V of xi minus xj. And in many cases, we assume more. So, it only depends on the distance between two particles in R3, xi and xj. So you can put absolute value in xi minus xj. And final basic law is the Schrödinger equation. So we have I partial derivative psi t equals h psi t. So, it describes the dynamics. So the question typically is like we have an initial data like this when t equals 0, and it evolves according to the basic law, in this case the time-dependent Schrödinger equation, and we will find the result or the dynamics. And so in this case the initial data is factorized, and this means that the psi 0 is written by the product of phi through I equals 1 to n, and all the phi's are normalized so that the L2 norm is 1. Then what is psi t? Formally you can think it as like e to the iht times psi. So formally you can believe that psi t equals e to the iht psi 0. So this will evolve this initial data. But in this case, this is kind of meaningless, or it does not say much. Yeah.
Unfamiliar to us. What is V and what is delta I?
Oh, this delta is Laplacian. Yeah, Laplacian. So, yeah. Yeah. Oh, I is Laplacian with respect to the first ith particle.
What is V?
V is potential. So, well, so it depends on the problem, but in this case, you can think it as a compact. So, well, the typical shape of V is like this.
V is a function?
V is a function. V is a function. Some function. So you can think it as.
Each particle xi is a function of t, right?
Oh no, particles are very.
T is a time variable, right?
T is a time variable, but you can think it as a parameter. Yeah. So well, when I wrote this Schrödinger equation, I partial t times psi t, you can think it as a variable because I used the notation like the derivative with respect to the time. But because when you want to define the wave function, you usually define it in the space R3n. So that's why I omit this t here. But if you put t here, then it's kind of ambiguous.
This is a parameter function.
Yeah. So you can think a family of functions that changes through the time. So so this is Schrödinger equation, and this is initial data, and we want to consider this psi t, and we want more than this formal solution. So if you differentiate this with respect to t, then you get I times h. So h is here. So this can be the answer. This can be the answer. But we want more. And actually, physicists have an answer. So the answer is that this psi t is almost like the product of phi t, and this phi t satisfies this equation, I partial t phi t equals minus Laplacian phi t plus v convolution phi t squared times phi t. So this is not a linear equation, but this is nonlinear equation. That's what you call Hartree equation or nonlinear Schrödinger equation. So we can track each particle by using this Hartree equation, and then the final result is almost like this phi t, the product of phi t's. So that's from the theoretical physics. And their argument or heuristic is that, we can consider effective potential that a particle feels. So if you consider the particle number 1, x1, then it feels potentials from each other particle, so that the potential is V times this xi minus xj. And then, we also need to consider the density. So the density of particle is given by the square of wave function. So the square of wave function. So this is density, and this is potential. So if you multiply density by potential, then this is the potential that the particle x1 feels. We need to summation. We need to make summation over the indexes from 2 to n. And because the mean field limit has this 1 over n factor in front of the potential, we also need to multiply it by 1 over n. And then, because the summation does not mean anything, it just means n minus 1 times this integral. So we have n minus 1 over n. And, this is the definition of convolution. So v times phi t squared. V convolution phi t squared. So this is the effective potential. And then you can use the Schrödinger equation for one particle. So this is this. Of course, this is not mathematics. So first of all, the assumption is wrong because, to do this, we first need to let this psi t is the product of that wave functions of each particle, but psi t is not factorized. If you plug in the formula like this, then the Schrödinger equation, this I partial t psi t equals h psi t, is wrong. That tells us it is not equal to this, the product. But, nevertheless, we believe physicists. So their intuition is somehow right, so that psi t is approximately factorized. So psi t can be written as the product if you find a suitable approximation. Then the job of mathematical physicists is to make a sense. So the second problem is in which sense the above approximation holds. And the first intuition for mathematical physics or quantum mechanics is to use L2 norm, because L2 space is a Hilbert space, and every wave function is described in L2 space. So the first guess is to make L2 norm so that psi t minus this product will converge to 0 if you take the L2 norm and then take the limit as n goes to infinity. Unfortunately, this is wrong. And, well, in many problems, taking L2 norm cannot give anything. So it is usually wrong.
So the goal is you want to find P of T, right?
Oh, well, actually...
No, the primary goal for this problem is to find the wave functions.
So, well, actually, phi of t, phi of t is given by this Hartree equation. This must be right.
So you're assuming that if psi t is the product of functions of one variable,
then this is right. But then this is almost true, so that this phi t should be the answer. But then, so our goal is to prove something like that this psi t is very close to this product. And then the goal of mathematical physics is to give a meaning, mathematical meaning, and make a mathematical proof of this equation. Yeah, so well, if it were true, then this indeed is a very good theorem of mathematical physics, because we found this is almost like this in this sense, in L2 sense. So we gave a proper sense to this problem. And, well, I'm not going to introduce the proof itself, but, well, we want to prove the given result by using mathematics and the basic axioms, basic laws of this problem given by physicists. So, well, it's always like this. The basic laws are given by physicists. Physicists know the answer, and it can be a conjecture for mathematical physicists. And we want to give a sense by using mathematical physics or mathematics like this, and prove it by using mathematics. That's what people do in mathematical physics. And, well, unfortunately, this is wrong. So that's why we need to introduce some other things to find the sense of this approximation. So the sense is like this. So we need to define the density matrix. Well, if you're familiar with quantum mechanics, then perhaps you know the concept of density matrix. But it's like projector or operator, so that. So I think, well, this operator is easiest to understand. So well, this phi t and phi t means that if we are given a function like chi t, then, well, this operator, the projector, returns let's use chi. So the inner product between this phi t and chi times phi t. So it indeed is a projector. So, well, this kind of density matrix gives, well, this kind of result, so that if you plug in a state or a wave function, then it returns the eigenstate or eigenfunctions of a given operator with some suitable constants like this. So this is n-particle version of projector. So if you have psi t, then this times this as a kernel form. And well, if you have n particles, then there is no hope to find the right sense of the approximation of the former first slide. So we have this one particle marginal instead. This means that we want to cancel the effect from the x2 to xn particles. So we only have this gamma t of two variables, x and x prime. And to denote that it is one particle marginal, we put this one here. So this is, well, this describes the behavior of this wave function. And we can just focus on one particle only. So this is derived from this n particle wave function. And also, we have an operator, this, which is derived by this phi t, the solution of Hartree equation. And we want to compare this and this by using this trace norm of the operator. And then, indeed, this converges to 0 as n approaches 0, or n approaches infinity. And we can prove even more that this the trace norm of difference is bounded by some constant, depending on t, over n to the alpha. Alpha is bigger than 0, and well, alpha is less than or equal to 1. But anyway, so if you let n go to infinity, then this part will become 0. So that's why this trace norm should converge to 0. And that's how we give meaning that this wave function, our target, is very close to this. So well, I'm not going to prove this, because this is kind of long, and so it depends on the type of potential. So when V is bounded, it is easy to prove. When V is L1 or L2, or well, if it's L3, then it is not proved yet. And if it's like Coulomb potential, like that V is 1 over x, then it is proved, but alpha is not 1, but it is 1/2. So well, the result so far depends on the type of potential. But anyway, so we have this, and this is what mathematical physicists do. No, n goes to infinity.
No, capital N is bigger than 1.
Oh yeah, of course. Yeah. So well, it is. Yeah, it is number of particles. So we have x1 through xn. So n is always integer.
No, bigger than 1.
When n is 1. Well, but then we don't have any potential term here. So this is just free particle with just Laplacian. So, yeah. Well, I think he can make a mathematical problem, but it's not interesting, I guess. Yeah. So, any other questions? Okay, then here's the second topic or example, or well, second chapter of this talk. So well, in this case, the theme is ground state energy of Bohr's gas in the low density limit, which means that we have a box, three-dimensional box of side length L, or you can think of a torus for just technical reason. But well, if you just want to consider a physical system, then you can just think it as a box of side length L. And we again have particles from x1 through xn, but in this case, the particles are confined in the box lambda. The wave function psi is again an L2 function, but in this case is L2 of lambda n. So lambda is a three-dimensional system, a box. So well, it corresponds to R to 3n, but in this case lambda to the n. The Hamiltonian does not contain any 1 over n. So this is just kinetic energy part, the minus Laplacian, and the potential without 1 over n. But again, you can think V as a function like this. So you can assume that it only depends on the distance between I and j, and this is bounded, compactly supported. And for some problems, you can also think V as repulsive, or V is non-negative. Well, Schrödinger equation in this case does not involve any t, and well, it's time-independent Schrödinger equation, h psi t equals e psi t. So you can think it as an eigenvalue equation. So h is an operator, e is an eigenvalue, and well, this gives energy. We also consider limit as an approaches infinity, but in this case, because we had a box of sidle length L, we want to let L go to infinity as well. So the way of doing it is first to fix this rho, the density, which is defined by n over the volume, is fixed, and we let those two variables go to infinity. And this low density limit means that the density rho also goes to infinity, but well, in mathematics we need to be very careful when taking two different limits. So the order is to take this limit first and then this limit. Or you can think it as taking limit, this thermodynamic limit only, and rho is just a small number, which is very small. So the question is, what is the lowest eigenvalue of this equation, or the ground state energy? So there's an history.
E is a number, right?
E is a number, yes.
H is an operator.
H is an operator. So that's why it is an eigenvalue equation.
E0 is the lowest eigenvalue.
Yeah, the smallest one. So, well, in 1947, Bogoliubov first analyzed this system of interacting bosons. Well, I'm going to omit the description of bosons and fermions here because that's just physical. But, well, and also it's irrelevant here because the ground state energy of both gases is just the same as the ground state energy without any any conditions. But, well, for physicists, it is meaningful. So, it's interacting bosons. And in 1957, Lee and Yang derived the ground state energy for particles in a low density limit, and they found a very long formula like the E0 of n, the energy per particle, is 4 pi a rho. A will be explained later. And 4 pi a rho times 1 plus these messy terms. And A is the scattering length of V. And this is not rigorous because they made some assumptions that cannot be proved in mathematics. So Dyson, who was someone like mathematical physics at the time, wanted to prove it without any of those assumptions. So for the hardcore potential case, the hardcore potential means like this. So this is V, and this is A. So for example, this is A. This is like this. So V is infinity. V of x is infinity if the absolute value of x is less than some number, and this is 0 otherwise. That means you have a kind of ball, like billiard. So if you have two particles, then it has a certain volume, and two particles cannot be closer than some distance because each particle occupies a certain volume. And if the particles are separated by a distance which is longer than that distance, then they don't feel each other. So infinity or 0. in that case, the ground state energy per particle is less than 4 pi a rho times 1 plus some small number, small factor. And it is bigger than 1 over 10 times square root of 2 times 4 pi a rho. So, well, mathematical physicists always want to use inequality instead of this kind of approximation or the equations. So, to prove that the ground state, the first term of the ground state energy is 4 pi a rho, people in the mathematical physics want to prove this inequality, and this is bigger than this. By doing so, we can prove that this equals this, at least for the first term. And Dyson proved this, the upper bound, correctly, and the lower bound is not good enough.
Very low.
Very small, very low. Yeah. And almost 40 years later, Lieb and Ingwersen proved the correct lower bound, like 4 pi rho times 1 minus some small factor. So, well, this is only for V is bounded, compactly supported, and non-negative. So it really looks like this. What I did for this problem my first paper was to prove that this is again 4 pi rho times 1 minus small factor when we don't have this non-negativity condition. So in this case, we can add some negative parts like this. So, well, adding this small change means a lot in this kind of problems. And then people tried to prove this second term of this equation. Well, as in the first problem, we believe that this is correct. We only want to prove it. So, well, again, to prove the second term, we need to prove that this is bigger than this and this is lower than this. And, well, some other terms as an error must be very small, much smaller than this. And Yao, my advisor, and In proved this upper bound. This law. And my second work with In was to prove the lower bound for the second order correction term. And so far it is the best result for the lower bound, but it is not the optimal result we want to see, like rho to the 1/2. But so far it is rho to the 1/3 times some log rho. The log is very irrelevant because when rho is very small, this log is can be easily killed by this rho. So the important thing is this 1/3 and 1/2, but 1/2 is much smaller than 1/3 in this case. And I think I need to explain the scattering length. So when V, the potential is given, we define the zero energy scattering solution, which is the solution of this minus Laplacian plus 1/2 V times phi 0. And, well, of course, this is in three-dimensional case. And, well, the normalization is quite weird, but we have normalization that phi is 1 as x approaches infinity. And then the scattering length of this V is defined by this limit of x times 1 minus phi of x as x approaches infinity. So well, to understand this property of this V, you can think it as like this. So, well, V becomes 0 after some distance. So in other words, when x is large enough, this 1/2 V is 0. But then if 1/2 V is 0, then we only have this minus Laplacian times phi equals 0. But then there are only two different solutions of that kind of equation, that the Laplacian of something is 0. One is constant, and the other is 1/r. So every solution for this equation must be the form C1 minus C1 plus C2 over R, or absolute value of x, when V is 0. And we have this normalization condition that phi of x is 1 as x approaches infinity. So this C1 must be 1 because of the normalization. What remains is C2. But then if you calculate this thing, then, well, we have 1 minus phi of x, so we have this minus C2 divided by x. And then we need to multiply by x, so this x again disappears, so we only have minus C2. This is the scattering length. So in other words, our solution must have the form 1 minus a over absolute value of x. And the meaning of this is that if you have hardcore potential, like there, so V is infinity, if x is less than a and 0 otherwise, then if you calculate the scattering length, then it is V, it is a. So, well, if potential is given, then as you can see from those results, all other properties of potential will disappear when you calculate this ground state energy in the appropriate limit. Only thing remains is the scattering length, A. And for this hardcore potential, the scattering length was this A. It also means that, well, I said the hardcore potential is like the ball for billiards with some, that occupies a certain volume. And the scattering length is the radius of the ball, if you consider the billiard ball. So this logic means that we want to change all the argument into the case of hardcore potentials, at least physically. Okay, but then we need to prove upper bound and lower bound. Upper bound is very easy because, well, for any normalized wave function psi, well, if it's normalized properly so that this L2 norm is 1, then this psi times h psi must be bigger than the lowest eigenvalue. And the infimum, or the minimum of these inner products, is the lowest eigenvalue. So I think this is kind of a variation of a minimax property of linear algebra. So, well, what people do for the upper bound is to find a good trial function because of this property, so that if you find a good function such that this ratio is very close to the target we want to prove, then this automatically becomes an upper bound for this ground state energy. So, well, again, the very natural way of doing it is to consider a function of this form, f of xi minus xj, because the potential only depends on the distance between two particles. So we consider a function of this form that only depends on the distance of particles and make a product and find this thing. And if you make this f good enough, then this will give an upper bound. Well, actually, this method will give 1 plus rho to the 1/4 instead of 1/3. And to get 1/3, we need a very complicated wave function as a trial function. And finally, to get this result, it is even more. So we need to define a Fock space and a variational principle and change of number of particles. But, well, again, this is not a topic that I'm going to explain in this talk. So the upper bound is like this, but the lower bound is very hard. So Dyson was the first person who tried to find the lower bound for this problem, and he only considered a hardcore potential. So what he did was to convert this kinetic energy and this potential into a different type of potential. So, well, this is V. And, well, so if this is V equals V of R, then this X is R. So this is some number. And, well, the A is usually somewhere like this. But then, if you can convert this into a different potential, U, so that this is very small, like this. And this is very long-range potential. So, well, it's very long. And actually contains, so, well, the size of the support contains rho, like rho to the minus 1/3. So if you take the limit as rho goes to 0, then the size, not the size, but the size of the compact support will become infinity. But anyhow, so, well, very small, yet very long range. So he just converted this into a different potential, like U, and he just ignored all the calculation for this kinetic energy with the Laplacian or the gradient squared. Instead, he just used this different potential and minimized the potential by choosing the right coordinates. So, mathematically, it's like this. So he only considered the interactions between the nearest particles. So Ti is the distance between xi and its nearest particle. And then the new operator W is the scattering length times some suitable potential that looks like this, and xi only interacts with its nearest particle. And then he used some geometry to minimize this operator, U, or this function, by choosing the right coordinates of x1 through xn. And then he calculated this thing, the minimum of this function or operator, that gave this 1 over 10 times square root of 1 over 10 times square root of 2 times 4 pi a rho. Okay, so the next one is the lower bound by Lieb and Ingwersen. So, well, they knew that the Dyson's method does not work because of many reasons, but the one single most important reason was to ignore all the kinetic energy. So instead, they sacrificed almost all portion of the kinetic energy. So W is the same W as Dyson used. But instead, they kept a small part of this kinetic energy. Okay, so, well, H is bigger than this plus this. Epsilon is very small. But still we have that epsilon. And then use the perturbation, or Temple's inequality, like this. So the ground state energy can be calculated by the expectation value of this potential term with respect to the ground state energy, ground state ground state wave function of this H0 Laplacian without any potential minus some error factor. Well, then, it can give the correct lower bound. And there was one more problem using this perturbation theory argument because of this error term. So when we want to use the perturbation, we have two different operators, like this and this. And so if you have this kind of operator, then to use the perturbation, we want to say that H0, the unperturbed part, the main part, is much bigger than this part, the potential part. But then the problem is that we have a box, which is very large. If you have this box and Laplacian, then the ground state energy for this system is just 0 when the wave function is constant. And the first excited energy, or the second lowest eigenvalue, is proportional to 1 over L squared. So when L is not that large, we can just make this W very small so that this is much bigger than this, and we can just go on by using Temple's inequality. But then the problem happens when L is very large, and actually we are thinking of thermodynamic limit, and L must go to infinity, so it fails. So what they did is very interesting. So they used cell method, which is to cut the large box into smaller boxes, use the perturbation in each small box, and add all the energy from the small boxes, small cells. And again, there are some technical difficulties to distribute particles into different boxes and minimize the total energy by correctly distributing particles in each smaller cell. But, if you do the right thing, and if you use the super additivity, which means that if you have N1 particles and N2 particles in a box, then the ground state energy is bigger than the sum of energy for N1 particles and N2 particles. When B is larger than 0, everything is very easy, because if you just ignore the interactions between two particles, then the energy just decreases. And if you have smaller energy, it is always a good thing when you find the lower bound. It's not hard to find the right lower bound once you have this cell method and the super additivity. So that's how they got the lower bound like this. 4 pi rho times 1 minus c, rho to 1 over 17. That 1 over 17 does not mean anything. It's just for calculational purpose, and they mentioned that it's just irrelevant. It does not say anything about physics or mathematics. So in my first paper, I got rid of conditions that B is positive, B is non-negative. So if you drop this condition, then you can find some difficulties, some problems. First of all, we cannot apply Temple's inequality. It's a very technical reason, but, it's not a big problem. The second one is that, in the cell method, if you have a large box, you cut it into smaller boxes. We consider particle systems in each boxes, add the energies from these systems, then it will give a lower bound for ground state energy. Well, the problem is that when you cut this box into cells, we ignore the interactions between this particle and this particle. And ignoring was always good, because if you ignore some energy or some interaction, then it will give a smaller result. But the smaller result is also lower bound, so it's not a big problem. But in this case, there's no guarantee that if you ignore some interactions between particles across the boundaries, it will lower the total energy. Sometimes it will lower the energy, and sometimes it will increase the energy. So, what we do, well, so for template inequality, it's not a big deal because we can just use some other types of perturbation theory. It's just technical difficulty. For the second part, the idea was to move the grid for this division. It's like this. If you consider these two particles, then if you cut this box into cells like this, then we need to count the interaction between this particle and this particle. If our grid in division is like this, then they are in the different boxes. So we should not count this for the calculation purpose. So the idea is to consider the distance between these two particles and find the probability of having those two particles in the same cell. So, well, in some cases they are in the same box, some cases they are not. We find the probability of having those two particles in the same box, and we move this grid or this division continuously, and then take an average, and finally we multiply a suitable factor which comes from the probability of having two particles in the same cell. Well, the hardest part comes from that we cannot use superadditivity, so we need to prove that whatever number of particles we have, the ground state energy is positive. But I think it's irrelevant here. Finally, the lower bound for the second order term. Well, actually, that lower bound is much harder, and well, there are several new methods to prove the better lower bound, including this box doubling method. So conceptually, it means like this. When you want to find a better lower bound, you want to keep the number of particles very small and the size of the box very large. But in average, it does not make sense, because in average, if your size of the box is very large, then the number of particles is very large. So the idea is to consider small boxes first, because this box does not contain many particles. And then, when you want to have large size of box, then we add these boxes. So, well, to control the small number, we keep this box small, and then to have a large box, we put them together. So that's this box doubling method. But again, well, that's just technical difficulty. So, well, from these new ideas, we could prove the lower bound is 4 pi rho times 1 minus c times rho to the 1/3, instead of the optimal result of 1/2 times some rho.
What is rho?
Rho is the density. Yeah, so n is the given factor, in the original problem. So at the beginning, we only had this information, and rho was fixed as n over L cubed. When you take the limit, n and L approaches infinity, but rho is fixed. And then we let rho becomes very small. Okay, so here are some open problems that I'm working right now. So first of all, for the heart rate dynamics, I said, well, this thing is bounded by this, and this 1 over n to the alpha factor means that when n approaches infinity, this thing is bounded by 0, so that this becomes 0. So we know that alpha is 1. That's the optimal result for a large class of different potentials. So far, it is only proved that when V is bounded, V is in L infinity, this is 1 over n. When V is like Coulomb, so 1 over x, then this is 1 over square root of n. And, well, people believe that for Coulomb potential, it's also 1 over n. So this is the first one. And then the second one is that the results so far is only for the Coulomb potential or better. So, well, I didn't mention it explicitly, but the problem here, the difficulty here comes from the singularity of the potential. The decay or the long distance behavior is not a problem. So, well, of course, this L infinity, the bounded potential, is much better than this Coulomb in terms of singularity. And if V is in L2, so that if it is like 1 over x to the 3 halves, then it's even much more singular. So, well, in this case, that result of the heart rate dynamics also holds, well, it should hold, and we're going to prove it. And the final thing and the hardest thing is, of course, to find the right lower bound, because we know that this lower bound should be able to be 1/2 instead of 1/3. And, well, it will require some other techniques and ideas. So, yeah, that's it. And, yeah, thank you for listening.